Let's get the party started. Certainly want to thank everybody that joined us on YouTube tonight, our meetup groups. You know, we're on all sorts of social media. We're on LinkedIn, Mastodon, Instagram. I don't want to be on Twitter anymore or X all that much. We're on Facebook. We really try and canvas out there to get as many people as interested in what we're doing as we can. And so we do these online lectures every month, and some of them are in person, and we do get great speakers. And this month there's, we're very lucky to have this speaker, Dr. Bartusiak tonight. And, she's been combining her undergraduate training in journalism with a master's degree in physics. And Marcia Bartusiak has been covering the fields of astronomy and physics for more than 4 decades. She's a professor of the Practice Emeritus in the graduate program in science writing at the Massachusetts Institute of Technology. She's the author of 7 books, and I'll put some links into the chat here a little bit so you can see those. But she's written books on astrophysics and the history of astronomy, including Black Holes, Einstein's Unfinished Symphony, which was the winner of the American Institute of Physics Science Communication Awards, and The Day We Found the Universe, which we'll be talking about today. That is the winner of the History of Science Society's Davis Prize. In 2008, she was elected a fellow of the American Association for the Advancement of Science, cited for exceptionally clear communication of the rich history, the intricate nature, and the modern practice of astronomy to the public at large. And you'll see why, because we've been chatting with her since about 7:30, and it's just so much fun to chat. And welcome to the Westport Astronomical Society's lecture series. Please welcome Dr. Bartusiak.
Thank you very much. The idea that there were other galaxies in our universe is actually a very old idea. In the 18th century, William Herschel in Great Britain was using his big telescope, the largest in its day, and seeing all these nebulae. And for a while, he actually thought of them as other universes. And at the same time, the philosopher Immanuel Kant, who was very fascinated by this, called them island universes. But by the 20th century, all that sort of went away, and people just assumed, the astronomers at the time, assumed that these nebulae were just baby solar systems in the making. In fact, you can see here from a picture taken in 1899 by James Keeler at Lick Observatory. He did something a little different. While other astronomers were focusing on planets and stars, he decided to make nebulae his specialty, which was a real oddity. No other astronomer really cared about these nebulae at the time. So he started scanning the sky, and you can see there in the various circles where he was counting, and he was seeing thousands across the celestial hemisphere. But unfortunately, he died early of lung cancer. And so for a while, no work was done until this man, Heber Curtis, also at Lick Observatory in the 1910s, decided to take off where Keeler left off and continue to study the nebulae. And he used this great big fat telescope called the Crossley reflector there at Lick. In fact, it's still being used professionally at Lick, more than a century of use at the Lick Observatory. And he made the nebulae his specialty. And he was the man who almost discovered the universe, because he started seeing so many of these spiral disks on the sky. He figured there were probably 1 million around the celestial hemisphere. And he decided that they were distant galaxies. Well, what was the evidence that he came up with? First of all, he saw that there were these dark edges along the edge of the disk, just like the dark clouds in the Milky Way. He also was noticing novae flaring up occasionally in some of these disks. And he estimated that based on what we knew about the brightness of novae within our Milky Way, these were far dimmer. And he figured that they had to be millions of light years away in order to be so dim. So we had all this evidence. And you might think, well, why doesn't Heber Curtis get the credit for discovering other galaxies? The main reason is because it was all circumstantial evidence. He didn't have a slam dunk. He didn't have a measuring tape that he could take way out to that spiraling disk and determine exactly what the distance was. So he was left hanging for a while. He didn't have the tools to be able to determine the distance. But fortunately, around the same time in the 1910s, Henrietta Leavitt at the Harvard Observatory discovered the perfect tool that Heber Curtis needed. And she was a specialist in variable stars. She would look at various plates there at the big photographic collection at the Harvard College Observatory, and she would look for variable stars. She was a variable star demon. She discovered more than anyone else up to that time, thousands of them. And she noticed a particular star that is the Cepheid variable. And she noticed a pattern in the way they varied. She noticed that with the Cepheid, the brighter the star, the slower the period. The variable star is actually like breathing in and out, and it gets brighter and dimmer over periods of days, weeks, or months. And the brighter stars had the slower period. The dimmer stars had a faster period. And she had this famous, what's now known as the Leavitt law, the period luminosity law. It was a linear relationship. So once it's calibrated, that means that you could look at find a Cepheid variable in the sky, and you would count its period. You would watch it over days, weeks, or months and figure out what its period was. Then from this law, you would find out what its luminosity was if you were like right next to it. And then you say, well, it's much dimmer than that. So then you have a way using simple optics to determine how far away it must be to be that dim. This was just what astronomers were hoping for. And she found it. Suddenly, astronomers had a tool to see distances far, to measure distances far greater than they had before. Before this, various mechanisms like parallax, you could see a few, several hundred light years out into the Milky Way. Now, this was a way, because Cepheids are so bright, they can be seen millions of light years away. And so suddenly there was this astronomical tool. And one of the first to use this tool was Harlow Shapley. He grew up in the Midwest, and he actually worked for a while as a crime reporter when he was in high school, before he went to the University of Missouri and majored in astronomy. And from there, he went on to Princeton University to get his doctorate. And once he graduated, he went to the Mount Wilson Observatory in California, which then was the best observatory in the world. And he put Henrietta Leavitt's standard candle to great use. He was actually one of the first to take advantage of this new tool. And what he did was he measured the distances to all the globular clusters that are surrounding the Milky Way, like bees surrounding a hive. And he used the Cepheid method. And he discovered, one, that the Milky Way was far bigger than anyone had previously imagined, and that the sun was not located at the center. As he liked to say, the solar system is off center, and consequently, man is too. And our solar system is seen right there on the lower right. There where the cross is. That's where we're situated within the Milky Way. And he estimated that the Milky Way was many times bigger. Astronomers at this time in the 1910s thought that the Milky Way was maybe 10 to 30,000 light years wide. He decided it was far bigger. We now know that it's 100,000 light years wide. And this led Shapley to then devise what he called the big galaxy model of the universe. The Milky Way was the universe, suspended in a space of unknown depth. And everything else you saw in the sky were just little appendages surrounding the Milky Way. It was the big galaxy model. So by 1920, there were two completely different views of what the universe comprised. There was Shapley with his big galaxy model versus Heber Curtis, who was saying that there were other galaxies, other island universes. And they even had in 1920 a big debate in Washington, D.C. Over this. But the data was still very fuzzy. You could argue either way. So there were these two competing models of what the universe was. Now, Curtis, he could have continued at Lick. And, it could have been the Curtis Space Telescope. But he got offered a job at the Allegheny Observatory in Pennsylvania. They wanted him to be the director. This was a great promotion, to be director of an observatory. And he had a family, and he could use the extra money. So he packed up, left Lick Observatory, and went to the observatory that was just above Pittsburgh, Pennsylvania, where all the steel mills were spewing out smoke and gas and clouding up the sky. He never made another great observation again. And he knew it, that he was sort of out of the game because he just was not in a good place for observing the sky and continuing his work on the nebulae. So Curtis, out of the game. Now, it could have been Shapley. Shapley could have continued his work using the very same method, using the Cepheid variables, seeking them out farther beyond the globular clusters. And he could have discovered that there were other galaxies. But no, he refused. He was wedded to his big galaxy model, and he didn't want to hear anything about island universes. So he got out of the game as well and went on to the Harvard College Observatory to become its director. So it could have been the Shapley Space Telescope, but no, Shapley would learn to regret that after a while. So enter a newcomer to this game. He arrived at Mount Wilson in 1919, straight from serving as an Army major in World War I. The observatory's director, George Ellery Hale, was always on the lookout for good people, and he was aware of Hubble's PhD work at the University of Chicago and promised him a job once he finished up serving in the Army during World War I, where he rose to become a major. In fact, a lot of people always called him Major Hubble. And at first, at Mount Wilson, when he arrived in 19, he stood in Shapley's shadow. Shapley was the golden boy. He had discovered the Milky Way and our true place within the Milky Way. But once Shapley went off to the Harvard College Observatory in 1921, Hubble was able to focus fully on the spiral nebulae, and he had the field pretty much to himself. Now, Hubble was a complex man. Friends called him an Adonis. He was kind of handsome. I always think he looks a little like Jeremy Irons, the actor Jeremy Irons when he was young. He grew up in the Midwest, just like a lot of astronomers at that time. The sky was really beautiful and grabbed a lot of people at that time. And his father was in the insurance business. And he went to the University of Chicago hoping to major in astronomy, but his father put his foot down and said, no, you are going to become a lawyer, and insisted that he study the law. So Hubble obeyed his father, and though he took some courses in astronomy and physics, he did do some pre-law as well. In fact, he did so well in his coursework, he became a Rhodes Scholar, going over to the University of Oxford in Great Britain for 3 years. There, in Great Britain, he completely transformed himself. He began to speak with a British accent, which he did for the rest of his life. It drove the Mount Wilson astronomers crazy. He learned to brew a proper cup of tea, and he wore a black cape all the time with a great flourish. And as you see here on the right, he took to wearing knickers. This was from his British influence. This was his standard observing uniform. When you see pictures of him at the 100-inch telescope, he's often wearing his knickers. He was someone who yearned to be singular and distinct. He even added a bit of gloss to his resume. When he came back from Oxford and went back to his family, he always told everyone that later on that he gave up the law for astronomy, but actually he never practiced law. When he went back to the Midwest after Oxford, he actually taught high school for a year. He taught physics and Spanish, of all things. But during that time, his father passed away, and finally he had the courage to go back to the University of Chicago and start his PhD. And that is where he became fascinated with the spiral nebulae and made it his topic for his PhD dissertation. Well, upon completion of his PhD and his Army work, he showed up at Mount Wilson on September 11th, 1919, just a week after the great 100-inch telescope came online and started operating for observations. Then, of course, the largest telescope in the world. And he began using the telescope on Christmas Eve, 1919, and he kept this logbook to keep track of his observations, page upon page. I had a wonderful time in the Huntington Library in California. This is where all of Hubble's papers are kept. And it was so exciting when they handed the logbook over to me across the counter, and I couldn't believe they were allowing me to look at it. I spent the entire day looking page by page to mark what he was doing and what he was looking at and how he was assessing the sky. And he told a colleague he was going to, quote, determine the relation of nebulae to the universe. He suspected that they were other galaxies. He wanted to prove it. And he did this with single-minded devotion. Year after year, starting in 1919, year after year, he would go from target to target, photo after photo. And each photo was labeled H for the 100-inch, the plate number in his sequence, and H for Hubble. And in 1923, he spent 47 nights on the mountain. And that was the year that something surprising happened. I'm going to read a passage from my book to describe that evening. October 4th, 1923. The seeing was poor, but it was good enough, just barely, to stalk some celestial quarry that autumn evening. As the giant scope swung around, there was a whine, a series of loud clicks, and then a final clang as the instrument was secured into place. Hubble examined M32, a small and roundish nebula, for a while, and then he maneuvered the telescope just a fraction of a degree to photograph M31, the famous Andromeda Nebula, the target of choice in the island universe debate. By then, the seeing had deteriorated to a point that other astronomers might have closed up shop, but Hubble persevered, and despite the mediocre viewing, soon noticed a new speck of light within Andromeda's cloudy veil. It was exactly what he was hoping to find one day as he conducted his extensive survey of the nebulae. Novae had been seen before in Andromeda. That wasn't startling, but Hubble was sure that additional sightings would help reveal Andromeda's secret. Nova suspected, Hubble neatly wrote in black ink in his logbook for plate H331H. And after photographing Andromeda for 40 minutes, he went on to observe another nebula, a barred spiral, before ending his run. He returned the next night and again saw the new pinpoint of light. Confirms Nova suspected on H331H, he wrote in his logbook. Here is the actual photograph that was taken 100 years ago this month. Once he left the mountain, he analyzed this photo more closely and compared it to other photographs of Andromeda that had been taken over the years. And by doing that, he spotted two more novae in this photo, but he also saw that one of those, what he thought was a nova, actually was brightening and dimming. It was a star that was brightening and dimming over time. He had found a variable star in Andromeda. Well, you can see how he X'd out the N and put in VAR exclamation point. He was so excited by this find. It was celestial gold. For here was possibly, if that proved to be a Cepheid variable, that would be the cosmic yardstick that would enable him to find the distance to Andromeda directly. Well, to do that, he started keeping track of the star's variability, and 3 nights in February 1924 proved crucial. There on the right side of the graph, you can see the 5th, 6th, and 7th of that month. He directly observed the variable brightening by more than a magnitude. It was a tremendous break. From the length of the period and the overall shape of the curve, he now knew that the Cepheid was a variable, that the variable was a Cepheid. And this is a rare type of star that is thousands of times brighter than our sun. This actually was his moment of discovery. He then went back to his notebook and added a note. Let me read again from my book. There is the little note he added. Customarily reserved, Hubble at this moment is unmistakably restive. He didn't write his message in black ink, which he regularly did for his records, but instead in pencil. And his handwriting, usually so fluid and precise, was more hurried and askew. He was obviously elated. Quote, on this plate, H335H, 3 stars were found, 2 of which were novae, and 1 proved to be a variable, later identified as a Cepheid, the first to be recognized in M31. And to highlight the addition, he drew this big arrow pointing directly downward at his historic news. And in its broad stroke, the arrow makes his excitement literally jump off the page. For once, Hubble, usually so reserved, dropped his guard and figuratively clicked his heels at this moment of discovery. Well, Hubble couldn't help but notify his nemesis, Harlow Shapley. They couldn't stand one another, but they needed one another. Hubble worked on the largest telescope in the world, and Shapley, there at the Harvard College Observatory, was director where there was the largest photographic plate collection. They needed one another. So notice that there at the top, that Hubble didn't open with polite niceties, inquiries of health. He got right to the point. You will be interested to hear that I have found a Cepheid variable in the Andromeda nebula. And then he went on to describe the technical details. He had had a period of 31 days, varied between magnitude 18 and 19. And here's the kicker. Using the very same formula that Shapley used for the globular clusters, he calculated a distance to Andromeda of some 1 million light years. Now, we now know it's 2.5 million light years to Andromeda, but this was before things were fully calibrated. But still, it was a direct and indisputable measure out to Andromeda. It was indeed a separate galaxy. Well, Hubble got in some further digs at the end. Quote, I have a feeling that more variables will be found by careful examination of long exposures. Altogether, the next season should be a merry one and will be met with due form and ceremony. Well, Shapley, upon receiving this letter, held it up in his office and told his colleague, here is the letter that has destroyed my universe. Shapley knew right away the game was over. He didn't let Hubble know that at first. He played around, said, oh, you got to check your calculations. You got to check whether it's really a Cepheid. But he knew right away Hubble won the game. Well, Hubble made that finding in February 1924, yet he held off publishing. Today, my gosh, it would have been on the internet within 5 seconds. But Hubble's greatest fear was being caught in a scientific error. And a colleague of his at Mount Wilson, a very good spectroscopist, Adrian von Manen, was insisting that he was seeing the spirals, like the Andromeda nebulae, actually rotate within galaxies do rotate, but he was saying that they were rotating fairly quickly. He was actually able to see the rotation in a fairly short amount of time. And this would have been impossible if the Andromeda nebulae was truly farther, so far away. If it was 1 million light years away, you couldn't see such an effect. So Hubble waited. He was trying to figure out where von Manen went wrong. He was pretty sure that von Manen had done something that made the interpretation wrong. But he couldn't figure it out, and he didn't want to make an announcement until he knew where von Manen went wrong. And he would have kept on waiting until the very influential Princeton astronomer Henry Norris Russell insisted that Hubble submit a paper to the next American astronomical meeting. And that is what he did. It was presented on January 1st, 1925. But Hubble was not there. He had Russell read the paper. It's my suspicion that he didn't want to actually, until he knew where von Manen went wrong, he didn't want to be physically associated with reporting on this news and let Russell do it. And that's the day, you might say, that the modern universe, a cosmos brimming with other galaxies as far as you could peer, was actually made official. Now, as the textbooks have it, Hubble went on 4 years later to triumphantly discover that the universe was expanding. Well, that's not quite the way it happened. Evidence that the spiral nebulae, not yet known as galaxies, but that the spiral nebulae were moving outward, had already arrived much earlier using this 24-inch refractor at the Lowell Observatory in Flagstaff, Arizona. It was due to this man, Vesto Slipher, who was the first to obtain the speed of a spiral nebula. He did this by attaching this spectrograph that you can see, it's on display at the Lowell Observatory, onto the 24-inch, and carefully obtained a spectrum of the Andromeda nebulae in 1912. So while Curtis was at Lick, taking pictures of all of those nebulae with the Crossley, Slipher was at the Lowell measuring their speeds. And he found out that the Andromeda Nebula was moving towards us, moving towards the Milky Way at 300 kilometers per second. This was an astounding speed. The most that astronomers had measured up to that time were stars moving maybe 40 kilometers a second. So this was 10 times faster than any star in our galaxy. And he went on to determine the speed of other nebulae that he could see with his refractor. And by 1917, he had gathered the speeds of 25 spiral nebulae. This was, I can't tell you, such an extremely difficult task. The faintest required up to 40 hours of exposure. That meant taking his little plate, photographic plate, and putting it back into the telescope night after night to gather those few photons to determine the spectrum and determine how fast it was moving. He found out that a few of the nebulae, like Andromeda, were approaching us. These are the galaxies within what we now know as the local cluster. But he found that most of the nebulae were whisking away. He knew this because the light from the ones approaching us were bluer. The spectrums were showing a blue shift. The light, as it approaches us, the waves get contracted, they become bluer. But the ones going away, the light waves stretch out and become redder. It's known as the redshift. And this was an amazing survey. And by 1917, this was before Hubble was just starting his PhD, Slipher was agreeing with Curtis that they were likely separate galaxies. In fact, he even suggested that they might be scattering. The spiral nebulae are scattering. A little hint at that thought of the universe expanding. So, the end of the 1910s, we had some spirals that were approaching us, but others were moving away. That was known. But was there a pattern to these movements? That was the question. And to answer it, Hubble teamed up with Milton Humison, who was a man who started out as a janitor at Mount Wilson, but started learning how to operate the telescope and became one of the best observers. His specialty was getting the spectra, while Hubble focused on the distance measurements. And by 1929, Hubble was able to determine a definite pattern in the flight of the galaxies outward, now known as the Hubble law. Double the distance, double the velocity. Triple the distance, triple the velocity. Goes up linearly. What's interesting, though, is that you have the velocity information versus the distance information. in this paper. And all that velocity information in this 1929 paper did not come from Humason. Humason was just beginning to start his measurements of the spectra. Most of that data came from Slipher. Hubble wrote it in his paper, used the data without citation or acknowledgement of Slipher really deserves half the credit. And Hubble, at this point, had no idea that this meant that the universe was expanding. He often commented that he left theory to the theorists. The correct interpretation of the Hubble law actually belongs to this man, Georges Lemaitre, both a mathematical physicist and a Jesuit priest. He predicted what Hubble found 2 years earlier in 1927. He published a paper saying that the receding velocities of the extragalactic nebulae are a cosmical effect of the expansion of the universe. 1927, 2 years before Hubble, he's talking about an expansion. Space-time was stretching outward and galaxies were going along for the ride. He did this by setting up a cosmological model based on Einstein's recent general theory of relativity. And he worked this all out. He even came up with a crude Hubble constant, what came to be known as the Hubble constant. He did all of this with the data that was then available. And you might ask, well, why don't we hear more about this? Well, he met Lemaitre that year in 1927, went to a conference in Paris where he met up with Einstein, and he excitedly told Einstein about his results. And Einstein hated it. In fact, he told Lemaitre at that time, "Your calculations are correct, but your physical insight is abominable." Einstein at this point was wedded to his vision of the universe, which was stable and eternal. He just couldn't wrap his head around the idea that space-time would be expanding. He obviously didn't know that much about astronomy to know that the data was coming in, that nebulae were moving and things were happening. No, he had the classical idea of a serene and stable universe. So no one else came to know about this idea because Lemaitre published in an obscure Belgian journal that no one read. And once Einstein tells you that your idea is abominable, well, you don't go around advertising it. So it wasn't until 1930 that Lemaitre's paper was rediscovered and finally given its due. Then and only then was Hubble's measurements interpreted as a universe expanding. And because of Lemaitre's role in this, finally in 2018, astronomers did agree to rename the Hubble law as the Hubble-Lemaitre law. Now I'm waiting for the Hubble constant to be called the Hubble-Slipher constant. And it's ironic because the man we most closely identify with revealing the expanding universe really didn't like the idea. As it was, in 1929, he says it's difficult to believe. He would acknowledge that this idea of an expanding space-time was the best way to explain what was happening with the galaxies. But he always called, in all of his papers throughout the rest of his life, he always called the galaxy speeds apparent velocities, in case a new law of physics snuck in and changed our understanding. Not too surprising. Remember, 1920s, this was the time that quantum mechanics was stepping in and overturning our classical view of physics. So Hubble was worried that maybe the same thing was happening here. Hubble actually was a doubting Thomas until the moment of his death in 1953. Take, for example, this comment he made in 1947, where he wrote a paper on the potential power of the 20-inch telescope about to open on Palomar Mountain in California. He said at that time, we may predict with confidence that the 200-inch will tell us whether the redshifts must be accepted as evidence of a rapidly expanding universe or attributed to some new principle of nature. He was still saying that in 1947. Historians of astronomy, Helga Krog and Robert Smith, suggest that this legend that we have that are in all the textbooks that he discovered the expanding universe was shaped by American astronomers desiring, quote, a founding father and a figure around whom they could drape a single version of the history of the discovery of the expanding universe. But we shouldn't forget, there were all those astronomers who came before him. James Keeler, Harlow Shapley and Heber Curtis, Henrietta Leavitt, Vesto Slipher, and Georges Lemaitre. But Hubble remains the central figure, for he opened an entirely new field of astronomy, modern cosmology. Hubble was only able to see a few tens of millions of light years into distant space. He once said, with increasing distance, our knowledge fades and fades rapidly. Eventually, we reach the dim boundary, the utmost limit of our telescopes. What he couldn't imagine were space telescopes, like the Hubble Space Telescope and now the Webb Space Telescope, taking us billions of light years back into time, seeing galaxies as they were just born very shortly after the Big Bang. Moreover, we've expanded our vision with X-ray, gamma ray, infrared, ultraviolet telescopes, even gravitational wave telescopes detecting vibrations in space-time from the most violent events in the universe, like supernova exploding or black holes and neutron stars colliding. It's a whole new universe since Hubble days, and I can't wait to see what happens next. Thank you.
Thank you. It was great.
That was really interesting.
Let's get on the bandwagon. Join my campaign to get the Hubble constant renamed.
That was something that I was going to ask you too, is that why don't we know more about Slipher? I mean, he seemed like really, why is he not a household name? I was surprised. I'd never even heard of his name.
You have never heard of Vesto Slipher. He has been lost to history, and mainly because he was a very modest man. When he was discovering all these speeds of the nebulae, somebody from the Proceedings of the National Academy of Sciences wanted him to publish a paper giving, reporting on this. He mainly only reported in the Lowell Observatory newsletter, which people did read and it got circulated, but it wasn't the astronomical, the astronomical journal. It was astrophysical journal. It wasn't the monthly notices of the Royal Society of Great Britain. He just did his observing and kept to himself. He rarely went to meetings. And he didn't network a lot. And that's part of the problem. Hubble, he knew how to handle publicity. He got the New York Times to report on what he was up to with his discovery of other galaxies. And Slipher, he didn't go out and, make big statements. And also because, Hubble took center stage and, didn't even acknowledge Schleifer's work in that big important paper. In fact, there was such a backlash from his fellow astronomers over this that in his next big paper, he did credit Schleifer to those velocities and give him a pat on the back, but it was too late. By then, Hubble had taken over, and he'd taken over the whole story. So, yeah, that, and now I was trying to get back so I could see you all, and I'm having a problem again.
That's all right. I can ask you a few of the questions here that are starting to come in.
Okay.
So, yeah, I was going to ask you a little bit too about Henrietta Leavitt. And,
Oh,
you know,
yeah.
I only know of her just recently. One of our other speakers that we had started talking about her, and that, you know, and it's just recently that we're kind of hearing so many women that have really contributed to science, but were really relegated to the back as often as they were.
This was such an important tool. In fact, there was someone who wanted to nominate her for a Nobel Prize.
Right.
This is how important her astronomical tool was the ability for astronomers to measure distances far beyond the Milky Way. This was amazing. And this person, I don't know who it was, but he did write Harlow Shapley and inquired to get more information so he could put it into his nomination. But unfortunately, Shapley had to tell this person that you can't nominate Henrietta because she had died. She, in her 50s, got stomach cancer very shortly after her discovery of the period luminosity law. And the Nobel Prize is only given to the living. So it's possible that she might have been recognized in her day if she had lived on.
I didn't get a chance to recognize Monica Charmoy was the girl. She's a new WASP member, and she's a 16-year-old junior in high school, and she's been hanging out with us for quite a while. So she asked that question. One of these days, you're going to get to meet her. I think you'll like her.
Oh, I'd love that.
Yeah,
I'd love
so
that. That's, I became an avid. My love of astronomy started early, at the age of 7. So, you know, I know how wonderful it is to catch the bug at an early stage in your life.
Well, she's asked a couple more questions, so we'll throw this one at you. Do such heated scientific debates still occur today with our improved technology, or since we have more technological prowess, do we actually debate less now? But interesting question.
Good question. There are discoveries that come out that people question. There was that object that went by us, and it was claimed that it might have been an alien spaceship. That is being very much discussed within the community, though it's really gotten down to Avi Loeb at Harvard, the Harvard Smithsonian Center for Astrophysics versus everyone else who does not believe that you need to go that far to saying that there isn't a natural explanation for this unusual object. So debates do occur usually when the evidence is on the edge, when someone sort of makes a leap. This happened to some people. There was a group of astronomers who thought that they were seeing evidence of some polarization in the cosmological microwave background, and were declaring that they were seeing evidence of inflation, really direct evidence that inflation did occur to have our accelerating universe. And that got into a big debate that finally worked against them. They did jump the gun. It turns out that some of their data was contaminated because they didn't interpret the dust in the intergalactic space well enough, and they had to take back their results. So sometimes these debates do occur. Whether one goes, well, today we have the dark matter debate. That's been going on for decades, much the way the debate about spiral nebulae went on for decades. People are saying it's a particle that we have yet to discover. an unknown particle, maybe a supersymmetric particle that they have yet to discover at CERN, or a particle accelerator, but they're trying. There are underground detectors that are trying to find these new particles. But then there's another group that are saying that maybe it's simply that Newton's laws of gravity change over time or over space. The farther away you go, the gravitational constants change. So there is this great debate between those two sides over what is the dark matter. Is there new physics involved that makes us think there's matter there, or is it a particle yet to be detected? So that debate has been going on for decades. So yeah, sometimes this still does go on today.
You want to talk about go ahead, Cal. I'm sorry.
Yeah, how about the Hubble cipher constant, if you will? There's a debate about which the right value for that.
Oh yeah, the Hubble tension, because people who still use the direct method of Cepheid variables detect one Hubble constant. But you can also determine the Hubble constant through examining the cosmological, cosmic microwave background. And those two Hubble constants vary between, I think, 72 and 67 megaparsecs. I mean, kilometers per second per megaparsec. And each of them think they have the absolute perfect technique that is correct to, 5 sigmas statistically. And yet there's this difference. What is happening here? And they haven't figured it out yet. So that is a big debate right now over who is right, the people who are using the Cepheid variables or the people who are looking at the cosmic microwave background. And measurements continue to this day to figure that out. Maybe a gravitational wave telescope may, by seeing neutron star collisions throughout the universe, they will send out gravitational wave signals that may be useful in helping determine this as well. So stay tuned.
Hey, Dr. Bartusiak, if you stop sharing your screen, you'll be able
Yeah, I'm trying to get my mouse to work again. I think I cannot get it to work. I'm sorry. Just a minute.
Oh, that's okay. It's not a big deal. There's another question here for you too. This is from Stephen I don't have his
Schreier.
Yeah, Schreier. Okay. What's your opinion of communication satellites constellation regulation? And he wanted you to know that was an excellent presentation and very well appreciated.
Thank you. What are my thoughts about
communication satellites constellation regulation? So it's kind of coming down to regulation, throwing satellites.
Yeah. It's a toughie. I talked to one astronomer last year who says that because of global warming, ground-based telescopes may be seeing their day, that we may have to take everything into space anyway. Oh, good. Somebody was able to do this. Thank you for overriding me. My mouse it's always technology. So, if we get telescopes on the moon, then that won't be a problem. In fact, we'll have great views from the dark side of, the back side of the moon, I should say, not the dark side. And if we are going to have problems with global warming, with added pollution and whatever, it may be very difficult for astronomers to continue really good research from the ground, and may have to go out into space. So maybe in a few decades that will be a moot point. Right now, yes, they are hurting astronomers' views. The astronomers are going to the government to try to have some regulations on this. And they're also looking at different designs. If I read correctly, I think they're looking into the people who are putting up these satellites looking for other designs that will be less reflective and less of a problem. But right now they are, you know, they are a problem, and there's going to have to be discussions on this. I'm all for the astronomers getting the best sky they can.
Monica asked a really interesting question here too that I've never thought of this. So well done, Monica. So with gravitational wave telescopes, if you have those out in space, is there still going to be is there still an observable universe once you have that? Does stuff fall off the edge when you have a gravitational wave telescope? You know, because with optical, things eventually just get so far away that you can't see them again. But maybe maybe I'm spinning off here.
She's asking, since gravitational wave detectors can technically see farther away, greater distances with large collisions, does that expand the limit on how far we can see?
Thank you. That's a better explanation. Thank you.
Well, they will actually be our only way for seeing back to the Big Bang, because gravitational waves go through matter as if it isn't there. We are limited to seeing back to some 400,000 light years after the Big Bang, because you go to that point and the Big Bang is just one big plasma, and the light, you know, you can't see through that, just the way we can't see through the sun because of the plasma is scattering all that light. But gravitational waves can go right through. So the gravitational waves that were emitted from the Big Bang went through that plasma very easily. And they are now actually trying to detect this gravitational wave background, like the cosmic microwave background. This would be the gravitational wave background. These were the gravitational waves emitted from the Big Bang itself. And by detecting them and by analyzing them, you would go back to the very moment of creation. So yes, this is the one way through gravitational wave telescopes to see further back than we have ever seen before.
That's great. Thank you for clearing that up, Shannon. I really whiffed that. Is there any, is there any other?
Yeah, there was one other question that I didn't see answered here. You touched on it briefly, but Diogo Teixeira asked, what is your opinion of dark energy? What do you think it might be? Just your personal opinion.
Right now, it's a name. I mean, that's it. They have this effect in the fact that the space-time appears to be accelerating, not just expanding. And you need something extra. Now, Einstein's regular equations of relativity can explain the expansion, a uniform expansion, but it can't explain an acceleration. And they are, you know, giving it the name dark energy to explain this extra oomph. And some are adding back the infamous Einstein's cosmological constant, which does act like an anti-gravity and tends to make space-time expand faster and faster. That's one explanation, that you have to readjust Einstein's general theory of relativity, add this extra term, and voila, that's what it is. It's an anti-gravity. But there may be other ways of explaining this as well, and people are avidly looking, you know, with all this new data, with gravitational wave telescopes, with new measurements of the cosmic microwave background, they're trying to find clues. And how and why it arose, whether it's part of the Big Bang mechanism that put the universe into this condition, we still have yet to figure that out, and that's what they're going to be doing. But for now, we call it dark energy, and like we call it dark matter because we don't really know what it is, but it's a way of labeling something that we can talk about its actions and its behavior, but we don't know the origins or the source or the reason it's happening.
Well, let's go with one more question here tonight, and we'll turn you loose. But Monica asked again. You're doing her homework for her here. But these are great questions. Do these gravitational waves remain the same as they travel through large expanses of space, or is there shifts like redshift or light? Like, are they altered by the expansion of space-time like light is?
Good question.
She's a smart kid.
That's a good question. I'm trying to think if I've ever really thought about that. I do know that unlike electromagnetic waves, they are not absorbed or affected by matter as they go their way. They do go at the speed of light. They know that, at least so far as they have measured and determined, they are going at the speed of light, unless there's some small adjustment to relativity that occurs, when we dig deeper into the quantum nature of these waves. Actually, that's a good question. I think I'd have to ask a gravitational wave physicist, because I don't know the answer to that.
I love that. That's the kind of questions that we don't get asked all the time. Is I don't know. That is great. That's a home run question.
I would assume. I mean, it's an actual vibration of space time, and if space time is stretching, I would assume that the actual waves themselves would be stretching as well. But I'd have to find out what the physical mechanism would be.
That's cool. Well, I'll hook you up with her. You'll get her emails, sure, I'm sure, very soon. Steve Schreier just had asked too. Did you ever have a chance to meet Carl Sagan?
Once, and it was when I was starting out. Before I became a physicist. I was a TV reporter working in Norfolk, Virginia Beach, Virginia. Did that for 4 years right out of college, where I had majored in communications. And I did a story at the NASA Langley Research Center where they were holding a conference on Mars. And Carl Sagan was presenting his latest data on what to expect when they were preparing the Viking lander there in the early 1970s. They were preparing the Viking lander at the NASA Langley Research Center. The biology experiments were being set up there. And so they held this big conference, and Carl Sagan was there. And there I was with my camera and microphone, and I interviewed Carl Sagan. And that was the one and only time I met him in person, was that one time before I even was a writer on astronomy. So
that's great. That's
yeah.
What a cool guy to meet. I mean, we've all met some very interesting people, and it's so great to meet you too. And, I love that what we were talking about before we got live today is, when just it's science has come so far in 100 years, where we were talking about nebulas and things like that. And I was telling a friend of mine today that my grandfather went to school and he used a buggy. He grew up in San Diego, and he used a horse and buggy to go to his first few years of school. Well, he ended up, he worked for McDonnell Douglas, and he helped, he built some of the parts of the rockets that went to the moon. He worked on the Gemini or the Saturn V. He saw the Mir go up the hill to Palomar. I mean, he saw all these crazy things. All these things happened in 100 years. And for you to put this story together too about how science has changed so dramatically in 100 years, it's amazing. And what a great story you told us tonight. Thank you, Doc.
It is amazing. I first covered gravitational waves in the early 1980s, when it was only a blueprint on a bulletin board. And I interviewed Ray Weiss back in 1982, 83. And I remember thinking, as I was standing in front of that bulletin board, I'm never going to see this in my lifetime. I never thought that it was going to happen right away, because at that time in the 80s, Ray was very honest that, we don't even have the technology fully in place. This is going to take decades. And so I followed it for 3 decades and wrote a whole book on the whole history of LIGO and that effort. But that amazed me. I thought for sure we'd see dark matter by now. My first story on dark matter was in 1982 when it was still called the missing mass. And before it was even dark matter. And I thought for sure we'd figure it out. We'd find that particle right away. And now I'm, 4 decades later, and I'm still waiting around.
I hope we don't have to wait too much longer. So what a great talk. Thank you so much.
You're welcome. This was such fun. Great questions, everyone. Thank you for inviting me.
Well, we hope you come down and visit us down here in Westport. It would be great to have you. And you know, we'll work all this out again another time. Join us next month, and please give it up again for Dr. Marcia Bartusiak. It's been great. Thanks a lot, Doc. We'll see you soon. Bye-bye, everybody.
A sitting ovation.
See you now.
Good night.